All right, over to you.
Thank you. Hi everyone. I'm Vijay from IBM Research India. In this session, I will explain our work titled New Product Demand Forecasting for the Fashion Retail. And the authors are Vijay Ekambaram, Kushagra, Shumanta, Shravan, Satyam, and Vikas. So let's motivate the problem with an example. Let's consider a retailer who launched a new dress and it became extremely popular. So it became so popular that it soon ran out of stock. So he decided to quickly restock the apparel in large quantities to avoid further stockouts. But this time, the sales didn't go as he expected, and at the end of the season, he was left with a huge amount of dead inventory, right? So it's a new season now, right? And the same retailer is ready with a lot of new trending product designs. But based on his last experience, he was wondering if there is a more informed way of stocking up the inventory for new products. Specifically, he is looking for something that could enable demand forecasting for newly launched products, that is, for product with no historical sales data, for something that could work only given a product image, because these are for like retail products. I mean, the first thing that would come up with a product image and product attributes. So these are the available metadata for a product. And the third thing is something that could work with if any extra textual information like product attributes are provided. The fourth thing is, the tool should take care of other exogenous factors like holidays, promotions, etc. And the fifth is something that is explainable, right? So such a tool is what most of the retailers would be looking for, right? And that's where our work comes into picture, which is attention-based multimodal new product sales time series forecasting, right? So basically, this work is all about. Given that there is no historical sales data for retail products, specifically in the fashion domain, how do we enable a better forecasting, right? So the traditional norms that is followed in the industry is to, for any new product, they try to identify similar products. Which is kind of having very similar attributes, right? And based on by identifying the similar products, they try to aggregate the sales of those similar products and they try to match it to the new product, right? So basically, for every product, they try to come up with some proxy products which is having historical sales data, and based on that, they try to figure out the sales of this new product. But this approach, through various empirical evaluations, we understand that these kind of KNN based approaches do not capture the non-linearity dependencies between product attributes, product images, and other exogenous factors, right? So we need a method that could combine all of these together and that could enable a better forecasting, right? And that's where our work primarily comes into the picture. So in order to solve this, basically, just to formalize the problem. So given a product images and given product attributes and given exogenous data like events and calendar data, so this work, we kind of build an AI model that could predict the future sales time series for new products, right? So that's the high level problem formulation. And in order to solve this, we basically have five model variants in the increasing order of complexity and performance. And all these variants are RNN encoder and decoder based approach. So that in the encoder and the decoder, we fuse data from multiple modalities. So that to capture the nonlinear dependencies, right? And we can walk through these model variants one by one, right? So let me just quick check. Whether am I audible? Can somebody confirm that am I audible?
Yes, you
Yes,
are.
fine.
Yes, you are.
Thank you very much. Right. So the very basic variant that we have, this is the one with the least complexity, right? So we have a product image. We first pass that to to an image encoder, which could be anything like a CNN, which could get an image embedding out, right? So this could output an image embedding, right? And this image embedding, we kind of pass it through an RNN encoder and a decoder, where in the RNN encoder, we also encode events data. And if any sales data is available, we do it, else it is optional, right? So we kind of pass it through the RNN encoder that could output an embedding of it, which is then passed through an RNN decoder. And the RNN decoder just outputs the predicted sales, right? So this is the most trivial approach which anybody would think of. Let's say given we have data sources like product image, right, and other exogenous factors, right? Just take the image, pass it through an any kind of image embedding layer, and then merge it with an RNA encoder decoder and get a predicted sales, right? So when we evaluated this approach using various metrics, right? So we observed that the performance is not satisfactory, right? I mean, we see that the weighted MAPE or MAE or Pearson correlation, I mean, it's not up to the mark, right? I mean, so this is the first model that we call as a standard image RNN, which is the most trivial approach. So in order to improve this, we move to the second variant, which we call as an attention based model, where between the image and the image encoding we added an attention layer that could kind of attend to important portions in the image, which is kind of leading to a better demand forecasting, right? So it kind of attends to different portions, and what we observed is by adding an attention layer, we found that there is a good improvement in the accuracy of our results, right? So this is the second variant where which we call as an attended image RNN. By adding an attention layer, we try to reduce the noise in the inner feature space, right? So moving to the third model. Okay, so just to summarize, I mean, just to recap the architecture of the first two models, which are like standard image RNN and an attended image RNN, where we have a product image which we pass through an inception v3 and then an attended attention layer, and we have all the exogenous factors over here, then which we concatenate and which we use in an RNN decoder, which just keeps it recursively predicting the next sale point, right? So what we did next is the third variant, which we call as an attribute information, right? So the idea here is in order to the first two variants are just focused only on the product images, right? So that was the constraint that we had. Generally image starts coming up first, right? So given that you also have attribute information which could either be attributes like color, design, or it could be even textual attributes like the product title or product description, right? So if these information are available, then how well can we do better, right? So the first approach what we had is it's a trivial way. We just we just take the product attributes, come up with an text encoding approach, right? I mean, which could either be a word to vec or any sophisticated approaches like elmo or BERT, and that could output a word embedding which we could just concatenate with the image embedding and use it, right? So by this way, by adding an extra layer of information, we see that the accuracy further improved, right? But one important non-trivial aspect we would like to highlight here is that when we try to fuse multimodal data sources, it is not always guaranteed that the accuracy will improve. There could be scenarios where your accuracy drops by adding noisy features, right? So in order to do that, what we enabled is a residual connection, right? So this is the variant 4 where we kind of combined multiple features through the residual connection, right? I mean, similar to the residual CNNs and other, right? So by this way, what we achieve here is we do not go, I mean, the accuracy doesn't drop, I mean, compared to the initial baselines, right? So we kind of had an residual connections between the image and the text layers, and we observed that the accuracy further improved, right? So the last variant, okay, and here is the architecture of the residual multimodal RNN, where we have the text embedding, which will output the text output, and we have an image layer which output the image embedding. Then these are concatenated via residual connection, which is via this residual block, and that gets combined with all the other exogenous factors, which feeds into the RNN decoder, right? So the final layer is what we call as a cross attention layer, where I mean, since there are multiple dimensions, right? So we have dimensions with respect to text, with respect to image, with respect to other exogenous factors, right? So I mean, so we wanted to kind of have an attention at each of these dimensions for a better explainability, right? So this cross attention layer, what it does is it tries to combine these multimodalities in a different fashion by giving attention weights to each of these modalities separately, right? I mean, to either to the text layer versus the image versus the temporal layer, right? And I mean, this model gives the better accuracy, but more than accuracy, what this could give is a better explainability, right? So if somebody wants to understand why is this sales going high, I mean, so there are different layers of explainability that our work brings in. One is on the various at a feature level, and if you see that since it's a holiday feature is high, this is leading to the a better explainability for why the sales is going high. Another layer of explainability comes from, I mean, whether which features are contributing more, whether this is the temporal features or the image features or the text features, right? So, and from this graph we observe that the temporal weights are kind of getting more priority, and these are all like local explainability, right? I mean, for every particular prediction, the prediction, the explainability output changes, right? So, and these are the five variants that we kind of propose as part of this work, right? And to just summarize the results, right? So we compared our work with the standard Canaan approaches, right? The one which I mentioned earlier, right? So let's say for a product, if you want to figure out for a new product, if you want to figure out the sales, the predicted sales, right? So you figure out proxy products from your past data and use those as your surrogate values, right? So we had models like category knn or color plus category knn, and also the embedding knn. I mean, these are the three baselines that we had, and we compared that with their RNN approaches, which could be a standard image RNN or an attended image RNN. And we found that our results are comparatively way better than these knn approaches. The reason being, our approach could model the non-linearities that could happen in multiple dimensions, right? So that's the benefit of using RNNs in an attended way, right? So we also continued a comparison and also compared it with concatenation, multimodal RNN, residual, and the cross attention RNN. And we observed that the cross attention and the residual RNN were performing best, right? So just to kind of showcase how the accuracy or the correlation improved over different model, this slide could be a good example, right? As we start in the beginning, the Canaan models were trying to predict around the mean, but not trying to capture the trends. But as we go towards the higher variance of the model, what we observed is that we're able to capture the trends more accurately, not just the mean, right? So that's the benefit of our approach, right? So just to summarize, I mean, while the lot of classical time series forecasting methods, they're like univariate methods, right? For every time series, they have a model. In contrast, what we do here is we just try to build one model for all time series together, right? So that, I mean, that's the another benefit of modeling it via RNN encoder and decoder, so that every product is kind of captured as an attribute vector, right? Which also gets learned over a period of time, and you merge it with other exogenous data and the other temporal data, right? So the idea of what we're trying to do here is we're just trying to build one model which could predict the sales time series of all things together, right? So that's the first summary point of this work, right? And the second summary point here is we empirically study the effect of various network choices in modeling the image based new product time series as an encoder decoder problem, right? So here we have multiple modalities like image, text, and other temporal factors, right? So in this work, what we basically do here is we try to understand various network choices and how each is trying to affect the performance of the modeling, right? And we try to provide the output of it, right? And the third point is on, we also try to understand the impact of various neural network based multimodal visual techniques, right? So when you try to fuse multiple data, right, I mean, we have to effectively ensure that the gradient flow is kind of better, right? So I mean, we can try to understand that you by adding a residual connection,
Just
and we try to get,
one minute, yeah, VJ.
yeah,
You've got 1 minute left, yeah.
sure, yeah,
Yeah, I think you're summarizing already anyway.
yeah, I'm about to end, yeah. So the fourth point is on, we discuss the impact on various self-attention and cross-attention techniques, right? So how these attention techniques are bringing into explainability, right? And the last summary point is we kind of conduct experiments on a large-scale fashion data sets, which is having like 45 categories and around 10,000 products, and we report our results and findings, right? So I mean, that kind of summarizes this work, and this could be an interesting work where I mean, where in industries currently, I mean, they try to use the proxy products to figure out the sales of the new products. We try to propose a mechanism where we could use other multimodal data like product images, textual data, and all of this together and have a better encoding schemes so that we can still do a better prediction of new products. Uh, I think I kind of covered it. Maybe I could open it for questions. Thank you.
Okay, all right. Thank you very much, VJ. So we're at
Thank you.
about 20 past 10. I'll probably take, we have probably time for one question. This is no fault of VJ. To be honest, he was spot on. It's just that we started the session a bit late at 4 or 5 past 10. So
Yeah, no issues.
we've got some questions in the chat. Does anyone have a question they'd like to ask VJ on what he's just spoken about? No questions?
Sounds good.
Um,
Yeah.
Okay, I noticed there were a couple of questions in the chat. I don't know if you have access to the chat, but I see, I don't know if it's a colleague of yours or someone, but there's been at least an answer to one or two of them. Is there anything in the chat that you see, VJ, that you want to pick up on?
I'm not sure if I have access to the chat.
It's a
Mm,
button at the bottom. You should be able to just click on it. Okay, well, that's fine.
okay,
If
I think
not,
maybe
and we have no questions.
I could do it offline. Maybe I could just answer those questions
That's
offline.
fine. That's absolutely fine. Yeah. So let's carry on. So thank you very much, VJ, for quite an insightful talk, and in an important area of new product demand forecasting. Our next speaker is Carlos Eduardo. Carlos, are you there? Can you hear me?
Hi, Devon. Yes, I'm here.
Hey, how are you?
I'm okay.
Yeah,
Thanks.
welcome to this session. Can you test out whether you can load up, share your screen, and all of that?
Sure, I will. Have the option, I think. Let me see. Oh, yes. I found it. Yeah.
Found it, yeah? Okay.
Can you see it now?
Yeah, something is coming up. That's correct. Excellent. So we're 22 past. So whenever you're ready, feel free to proceed. I'll give you a heads up at 5 minutes to at quarter past when you're on 15 minutes, so you can at least get some questions at the end.
Yeah, sure. Okay, well, thank you very much for attending this presentation. My name is Carlos Rodriguez, and I'm a PhD student of the Center of Marketing and Analytics and Forecasting from Lancaster University Management School. My research is focused on using a machine learning algorithm for for retail forecasting for demand planning in retail. Last year, I presented the use of KNN with some promising results on this task. Now I will discuss a particular aspect of the algorithm for the same purpose. Well, the research is still in progress, so I try to summarize my findings up to date for a particular parameter that is required for k-nearest neighbor, that is the parameter k, the number of neighbors. Let me first introduce the topic on why I chose retail forecasting. Well, the importance of retail business here in the UK is very interesting from my point of view, because it concentrates 1/3 of the consumer spending at this time. And in 2019, retail business generated almost 400 billion worth of retail sales. And in 2020, with all the pandemic, the value only in food stores kept on 40 billion, only in food stores. So it's an important problem, an important topic, because most of the products that are presented or are offered for retail are presented in promotions, are offered in promotions. But the problem with promotions at this time is that the, the error is it goes from 30% to 140%. So it can be a large error if we are using promotions. And the other problem is that the products are out of stock twice in promotion. So the way to tackle this problem is to find similar promotions in the past, or to find analogous promotions from other products. But in the case I'm working on, this data set that was previously worked by one of my supervisors, we have a special behavior of the sales regarding promotions. Promotions are effective sometimes and not as effective as they were before. So that's the reason I tried to introduce this machine learning algorithm here. And let me talk a bit about K-nearest neighbors and why I'm using it. K-nearest neighbors is based on analyzing patterns from the past and using a finite number of these patterns to calculate or to predict a future, to predict the future, in this case, the future sales on retail. When I try to look at the literature, if it has been used for that purpose, I can see reduced literature about it. There are promising results on promotions. It's been used also for sporadic demand, but I haven't seen a complete development of the solution on K-nearest neighbors for retail. Now the question is, what is the problem behind it? To work with K-nearest neighbors, I need to define a number of neighbors. How many patterns from the past I require to predict a future situation? Mostly what they use, or also at the beginning, it was implemented with a heuristic rule. Let's say, for instance, K equal to 1, just one neighbor, just one situation from the past to predict. And as the algorithm has been used for classification purposes, there have been other techniques to define this number. For instance, using bootstrapping at the beginning and then cross-validation. So with cross-validation, I can evaluate a different set of key values. So I can say K equal to 1, 2, 10, 30, and then I make a decision about it. And this is what they do when they compare accuracy on train and test sets to say which one is the best one, or which one offers the most stable prediction. So my research question at this time is, what is a suitable search range for K? Do I need to evaluate a large range of values to make the decision because it's a time-consuming task? Or should it be defined, if I'm working with a data set with more than 50 products, should I define key for each product by separate, or maybe just one value for all the products? And another question is, as I'm working with promotional forecasting, is K valid for promotional periods and non-promotional periods? These are the questions. And the chart you can see in this slide is from a previous research for electric demand forecasting. It's from a work from Al-Qahtani and Cron. So I want to answer the question, the final question, because on my previous research, I got some promising results, but not a very good prediction for promotional periods. So if I use this pattern from Al-Qahtani and Cron, that I can see that some behavior is repeated from the past and in the future, I could use that somehow to define a heuristic to define the parameter, the meta parameter I need to make the prediction. So let me talk about the experiment. We have 60 time series, 60 items, weekly data, 3 years of data in average. Some products have less data than that. I have only 5 descriptors of sales. So I have days with promotions, some booleans about if there is a promotion running that week or not, if it's on feature presentation, if it's on shelf or not. So I have only those 5 descriptors. And I can see that the products are in promotions less than 50% of the time. This is the main observation of the dataset. And also the different impact of promotions. It doesn't mean that because it's in a promotion, I will have higher sales than when it is not. It can be the opposite. So it is a real data set, an interesting data set that I think it can be tackled with k-nearest neighbor. So what I did first was to extend it to 20 figures with additional information based on dates, based on also on the promotions. For instance, are we at the beginning of a cycle of promotions for several weeks? Are we at the end? Are we after a promotion? Before a promotion? So maybe I can add that information to the feature vector so I can perform a better prediction with k-nearest neighbors. So at the beginning, just to make the first prediction with k-nearest neighbor, I decided to evaluate with different neighbors from 1 to 30. So I chose different number of k using cross-validation to define the number of k. And I got, well, it was time-consuming task. And I also used 15 rolling origins to make sure that I am getting a proper prediction. So what we observe is that promotions are effective in overall, but also the deviation of sales is a bit higher when we are using promotions, and it is that expected. So the first attempt to tune the algorithm was to reduce the tuning scope for cross-validation. So I need to define how I want to explore, from 1 to 2, from 1 to 10, from 1 to 30. So how large should be that interval to the evaluation? I tried to apply a non-parametric test called the Nemenji test, the Friedman Nemenji test, and I found that it is possible to define some regions where the if I create a rank of the error, I can define that there are some intervals where the accuracy is not affected as much as I could expect. It is expected that the higher the value of k, I will have a lower MAPE, but it's not necessary at all. I can see that are certain regions where the error is similar in performance, or the accuracy is not as large as I would expect, because I would expect that the higher the search of k, I will get a reduced SMAPE in this case, but it doesn't happen. So I also could observe that there is a region where the values are quite stable. So I made the decision to do this experiment, what you're about to see, choosing k equal to 15. Well, what I found while using cross-validation is that it increases computing time. It is a large time that we require to when we apply cross-validation. I am using it for each item, so it is time-consuming. So if I can narrow this interval, I can get a better result. But I also observed that the value that I got for several cases was larger than the set of continuous promotional periods I can observe from the data set. So could I choose a different value than the one that offers cross-validation? Can I apply my own heuristic to do that? That's what I tried to evaluate. Well, the first what I did was to present, to examine the time series, and I could see that there are continuous.
Yes. You've got about 5 minutes, yeah? In fact, a little less, about 4.
Okay, thank you. Yeah, well, we can see that we have different well, continuous week with promotions. So I could say if I have only 4 groups of promotional periods in the past, and cross-validation says that I should use 12, what if I fix it to 4? And what if I use a linear combination between them to evaluate that? Well, what I did was to propose 3 scenarios for that. 5 features was the first scenario, the original data set. Then I extended to 20 features. And then I used a special algorithm that I found it useful the last time, that it was linear regression, to refine the features, to narrow the set of features as well. So in this case, what I did was to use the value that cross-validation gave me, also the new value that I got from the promotion cycles I could see, and some linear combinations. Well, the results were not as promising as I expected. I am still working on it, so I had this option in my mind, but well, these results in my mind, but I could see that again, even using the autoregressive vector that I added, I could find that not using it was the best option. So I could see that my extended dataset was enough to perform some good results. I decided to present only SMAP in this case just to make it easier, but this table can be larger with other errors. But the main observation was that it is possible to combine sometimes a different number than the one that cross-validation uses. But maybe I'm still, I can say, I'm not using the right way to do that. I'm probably using a value that is below that. Well, just to show you, these are the promotion cycles with the discount. These are the sales. And how does it perform with KNN? Well, if I'm using rolling origin, I can see that the values will change over time after I add a new observation. And it tries to capture the structure by using the extended dataset I offer. Just a little observation before finishing is that I could see, I don't know what happened here, but yes, the focus is on the number 10, is that the error can be minimized sometimes if I'm using an autoregressive vector, but the result cannot be as I expected. I mean that if I'm checking the 10th rolling origin on my dataset, is the one that has 0 sales and is looking for 0 sales in the past. So probably the accuracy depends on the extended dataset more than an autoregressive vector. Just to finish, my conclusions are these. Well, I could notice that using feature selection by calling to the linear regression algorithm was very effective. Again, the number of Ks I couldn't get a better solution than cross-validation, but probably for special events like promotions, I need to use a different one. That's something that is still in my mind because of the third scenario that I evaluated. Well, K-nearest neighbor chooses the best candidates. Not all algorithms have this possibility, but for a full conclusion, I need to evaluate bias and relative scale errors that it will be presented in my next presentation, hopefully, no, and also in the paper. These are some of the references I use, and now I open to questions if you have any, and thank you very much for attending.
Awesome, thanks a lot, Carlos. Quite interesting. Any questions from the audience? I noticed that we had some questions in the chat from Nicholas, so I don't know if you can see those questions in the chat or whether Nicholas wants to pose them directly to yourself. We've got about 3 minutes.
Okay. Yeah, isn't KNN very slow on datasets? I could say yes and no. For me, the most expensive the time-consuming part is based on the definition of K. The time series are not the problem. The problem is how many key figures you will include, in fact. And also, if you are using pre-processing, you have the pre-processed data before that, maybe it can save some time. Why key nearest neighbor and neural networks or TBUs thing? That's a good question. That's a very nice question, in fact. I come from practice, and I could observe a rejection of the practitioners when they were working with neural networks, because it was very difficult to understand. I am insisting on K-nearest neighbor because it's easy to understand. It's easy to implement. Even if you don't have the proper tools to do it, I can assure you that you can implement it also in Excel. So it's a convincing. It's very convincing to sell the solution if it works. Now, I cannot say that it will work on all the situations. One of the issues I had with K-nearest neighbor that each feature is okay. This is a very nice question too. I tackled that problem in my previous presentation. Pre-processing is basic for K-nearest neighbor, a proper pre-processing. I'm talking about centering and scaling can be done in very different ways. Mostly we can, in the literature you will find that you can divide by the max range, or you can divide by a standard deviation. It makes sense, but it can be also implemented in different ways. You can also add weights for that. No, maybe we can continue this discussion by email. But yeah, thank you very much for your questions. I think these are the two questions.
Yeah, I think it's plenty. I think Nicholas got in quite a lot of questions there, and you did an excellent job responding to all of them. So thanks a lot, Carlos, for your presentation. If you could just cancel the share screen, and then
sure.
It's over to me.
Thank you very much. Thank you, Devon.
No problem at all. Okay, I guess that then it's me up. Okay, now I need a bit of feedback. Can you all see my screen? I hope so.
Yes,
yeah, we do.
Yeah, okay, great. Because it reminded me of when I'm in the class, and I ask my students, can you see the screen? And there's about a 2-minute delay, and then you ask the question, is there anyone out there? So
but you're in edit mode. Oh no, yes, that's okay.
Yeah. Thanks a lot. Okay. So let me keep an eye on the time for myself. Got about 18 minutes. So thank you to the two previous speakers. Today I'm going to be talking about. This is actually I tend to present sort of I always say hot off the press sort of work, but just things that I'm sort of currently looking into, and this is some work that I'm looking into with a local NHS trust. They approached me some months ago because they wanted some help with drug forecasting. Still here or there about whether I should say medicine or drug, but for short, we'll just say drug forecasting. At the time, I think they met me because I was presenting somewhere else on something that was a bit completely different. I don't have any experience in drug forecasting, and of course, every domain area has its own appreciation that you need to have in terms of the characteristics of drugs, the purpose, the use for a particular drug, in terms of whether it's sort of routine medicine, whether it's a life-saving sort of drug. So there's an entire context behind forecasting for drugs within a hospital, pharmacies, and so on. The general agenda for today is a bit of data, straight away into the data and the context. I look back at because it was a learning experience for me, having really not done any sort of work in the pharmaceutical industry and so on. I'm still evolving what the research objective should be, to be honest. And just some quick experiments I've been running. I won't tell you when I ran them, but just some quick experiments I've been running, just so that I can provide some insight. Maybe some of the insight is obvious, and it basically just points me to future research, I think, for myself, but also something that's useful in terms of the advice that I provide to this local NHS trust. Okay. So got a bunch of data, sample data obtained from local NHS trusts here in the UK. They're doing things very simplistically, but essentially they want to improve their inventory management practice. They spend a lot of time with their staff, actual pharmacists taking orders and so on. And they want these people to do other things, basically what they're trained for, which is dispensing of medicines and so on. So they don't want them to be, worrying about inventory levels and these sorts of things. So that's the main issue. Initially, what they provided me with, there's a lot more data, but initially what they're working with and what they provide is just a small subset of the drugs. Each of the drugs have different clinical profiles, et cetera, but I don't really use it. I haven't really used that information as yet in the work. What do I have? It consists of historic dispense quantities in terms of whether the drug is dispensed directly to patients, individuals, or through particular wards across different hospital sites. And we've got data from 1st of April, so daily level, 1st of April 2014 to about 31st of July. But I've cut the end of the data a bit. I'll show you a little bit more on that a bit later. So this is not a big time series problem. We've been talking a lot about machine learning methods, and I did machine learning for quite some time, but this is not what this research is about. So I'm going to use sort of lots of statistical methodologies that you're familiar with, but also some new methodologies that have come up around in sort of the recent sort of 10 to 20 years, if that long. The results I'll be illustrating is on a single drug. And perhaps that's good because it just gives you an appetite for exactly what's going on by just looking at a particular time series. So they're looking to forecast at site level. Okay, they've got 3 sites, A, B, and C. Let's call them that. They actually have names, but I'll just call them that. And I've actually, as you can see, I've shrunk the data set. So I go up to the 21st of June rather than the 31st of July. So this is just a bit of a hierarchy in terms of what things sort of look like. Of course, you've got sort of total demand for a particular drug. Let's say this is drug A. You've got a number of sites. Each site has serves a number of wards. Sorry, the drugs at the bottom. So you've got a number of sites, a number of wards, and there's a demand for a particular drug A, B, or C at a given ward based on a given site in terms of the overall availability across those sites of the drug supply. So just a couple of time series plots. Sometimes we don't do that, but just to give you a feel for the data. So this is daily across the entire sample period. I wanted to break it down so you can see what it looks like by site. So site A, site B, site C. So obviously you can see the differing levels in terms of the unit demands. Site C is one of the bigger sites. Perhaps you can look at it as not the satellite site, but the main site. And they've got some smaller sort of satellite sites which are there for convenience. Again, all of this is probably for future research in terms of taking some of that information on board vis-a-vis creating better forecasts. Again, here, just showing you drug demand by type. So again, you can see drug A, for example, in quite high demand. You've got some drugs. So again, the time series have, depending on what level you're looking at them at, do tend to have a certain degree of intermittency at times. Okay. So this is just a look at the various drugs. This is a breakdown of the individual drugs by site. The data, again, this is, I like to see plots. I don't know about you all. This gives you a flavor for the situation. So you can see here that you have some sites where there is demand, and then obviously some sites where there's little demand, and then some sites where there's actually no demand. When I say sites, sorry, some wards. So some wards at particular sites. Okay. So if I sort of just did a quick sort of Pareto plot just to illustrate that better, and you can see sort of at the tail end of the plot here, there are several wards, which basically for this particular drug, it would appear that they don't issue that drug and there is no demand for that drug at that particular ward. Whereas there are some wards where the majority of demand exists. And so a question that we started out with, and one of the things we want to probably investigate, and probably it's a good time to acknowledge one of my co-authors, Nikos Korensis, because he's done quite a bit of work on sort of temporal aggregation and its use in forecasting. So one of the things we want to look into as well is whether it's possible to use some of this information across sites, across wards, and so on, to overcome some of the issues around the intermittent nature of demand and things like that. So a bit of a review, and I better speed up. I've got about 10 minutes left. Obviously, you know, the pharmaceutical industry is worth a lot. So this problem is important for the NHS. I think I don't have to mention that we're literally, you know, dealing with lives. But it was interesting to actually look at the forecasting that takes place in the industry. So this recent paper, 2021 paper by Louis et al., shows about 52% time series models and judgment. 24% actually using causal models. I don't think a lot of machine learning models being used actually, and about 19% using judgment. So generally the finding is, and this is supported by this pharma industry survey, which I referenced below, that the most popular forecasting methods are actually univariate methods. And so it's not just coincidental that this is the starting point for the local trust and for, you know, the sort of advice I'm trying to provide them. And basically, if they're not using judgment, which is a lot of what's going on at the local trust at the moment, then they're using exponential smoothing, some moving averages, and regression. So again, for those of us, you know, worked in industry, maybe some of you more experienced working industry, it never surprises that what we see in practice are sort of the very simple approaches. Exponential smoothing moving, you know, 82.1% of all the statistical forecasts that are being seen within this particular sector. Okay. Some other issues as well, they often is a lot of data, but of course the data is not demand, it's dispense or so-called sales data. And there's currently, what we're seeing is a limited use of upstream and downstream. So another area I'd like to take this research obviously is from a supply chain context to see whether we can use information between satellite sites, main sites and wards and stuff to see whether that can also improve not just the forecasting, but the decision making. Okay, lack of new models for increasing forecasting intelligence. So these are just some of the sort of the issues, some of the things that pop out when you look at the literature, just in case any of you are thinking of or already maybe in this area or thinking of getting into this area. So I stole this paper, stole this table from the same paper by Louis et al. And they just give quite a few recent papers, quite a bit of recent research. We've got the 2020 paper here, and they just, so you can just get a feel relative to the methods that I will be running for what is currently happening in terms of research and so on within this area. And so they're forecasting sort of 1 to 5 weeks ahead, 1 month ahead, 1 week ahead, some cases 1 to 5 years ahead and so on, typically focusing on metrics, forecasting evaluation metrics and so on. And as you can see, using mainly time series model with occasional multivariate information included. So what's the research objective? Really just to have a go, but okay, no, more seriously, I just wanted to investigate looking at, because of the prevalence of univariate models, this was a starting point for my advice to the trust. I just wanted to look at, you know, what do we have out there right now from exponential smoothing implemented in forecasting package and a number of other packages now supported through Fable and Sybil and all of that sort of stuff, to naive, to seasonal naive, to some of the more interesting methods based on temporal hierarchies, hierarchical forecasting, and so on. And I wanted to do an evaluation based on forecasting accuracy, but also on inventory performance. So what's the experimental setup? I must say these experiments are quite recent. I actually have not spoken to the trust about, you know, about any of this. There still has a lot of work to do before I can go back and say something, you know, that I think will be more robust. I need to look at some more data. But as I said, sample of 4 drugs, but I'm just going to illustrate some of my findings and so on on drug A, which you got a picture of previously. Okay, so daily observations in sample, I'm going 2,148 observations altogether up to 16th of February 2020 from the 1st of April. I've got 126, 126 observation, about 18 weeks holdout from February to June. I'm doing rolling origin evaluation both in sample and out of sample to estimate, to get a robust estimation of in sample errors, in particular the mean squared error in sample, but also to get a robust estimation, in particular to have a convincing evaluation, sort of moving the window along as we would do in practice in out of sample. They indicated a horizon of 1 to 6 weeks ahead, so about 42 days, and I'm looking at sort of 1 week ahead, 3 week ahead, and 6 weeks ahead. As we know, sort of typical error measures, MACE and MAE, I didn't want to go for the 7 or 6 different error measures. So I think these two have some consensus around them, although we can generally talk about the pros and cons of every single error measure out there. On the inventory side, I'm looking to sort of a standard order up to policy, review period weekly. And we can actually look at, so the current calculation is based on assumption of normal distribution, but again, I've also done previous work on that. We can actually look at the empirical distribution of the in-sample error. I just got a battery warning, oops. And the usual, I think, so if you're familiar with inventory modeling, the usual sort of K safety factor that relates to the target service level, we're looking at 0.8, so 90%, 95%, 99% all together. So this is sort of the, your standard setup for order up to policy inventory evaluation. So actually nothing too fancy. They actually have a separate initiative going where they're trying to develop some more interesting inventory models. But I'm going purely from a perspective of giving them an initial benchmark beyond just forecasting accuracy. So I thought this was a good starting point. Some of the methods that I'm looking at, dynamic harmonic regression. Facebook has a new methodology called Profit, so I threw that in there, STL decomposition with ETS. Hierarchical, bottom-up, top-down. I'm only using I didn't use the word hierarchy, so really these two evolved. These two basically give you the same result because I just have the top and then the side hierarchy. So I didn't need to have both of them, but the code was right there, so I just threw them in. I'm looking at trace minimization as well, then temporal hierarchies. Again, given the data, a lot of work has been done in these areas, and then a bunch of benchmarks, naive, seasonal naive, ARIMA, exponential smoothing, and so on. So some results. So again, this is not across the 1,000 time series or 1,000 drugs, right? So I'm not looking to generalize. I'm looking to just provide some insight. And based on what I've ran on the other drugs, which seems to stack up. So we've got a situation, for example, where the time series is quite messy. You've got all sorts of effects in there, holiday effects, they're closed on Sundays, all sorts of things happening in the data. And you have a certain amount of intermittency. Even sometimes when you aggregate up to weekly level, for some drugs, they're just not being ordered very frequently. So then it's not surprising, when you see this type of data, that on accuracy, for example, you see that the seasonal naive actually coincidentally does well. You've got the other measures coming in a little bit after both in terms of, so on the left, sorry, that should be MACE, and on the right, that should be MAE. When we look at the trade-off curves as it relates to inventory, just to point you out to the extremes again, so you see in sort of the bright blue, you see that seasonal naive comes in.
Hi, Devon. Sorry to interrupt. We're going to finish the session at o'clock sharp. So
at 2:00 sharp. Yeah. Okay. I'm gonna finish up now. So from the inventory curves, again, for many of us, if you've read inventory curves, what do you want? What stands out is if we look at scaled backlogs, that's effectively the trade-off between how much are you willing to keep in inventory versus having a backlog in order to supply a given service level. So the question for the trust is, okay, yes, you can use something like the naive, okay. But look how much inventory you're keeping in terms of the holding volume, but consequently you get a return in terms of service level. Alternatively, if we go back, I'm just going to see this one chart. If we look at the seasonal naive, whether this is just because of the holdout period, I'm not sure. I use a quite healthy rolling origin evaluation, but if you have some intermittencies and zeros in there, it's going to persist. But whether that's because of the case, you obviously see that the seasonal naive says it's very accurate, but when you look at the inventory trade-off, you see that there's quite a lot of backlog. It's holding, we've got low volumes holding, and then consequently, we have that low service level. So I'm going to jump to the discussion point, but that's effectively, you know, the story of what I've found, right? The story is that, you know, inventory metrics substantially different from accuracy metrics. I'll leave you with a quote that came up in one of the discussions that I was having with the staff there. So one of the guys who's the data science coder, he doesn't know much about forecasting, but he knows coding. He says, anyway, it doesn't really matter how accurate we are, right? And I think that was linked to the notion of, at the end of the day, they want to understand what is risk. And I think the biggest thing challenge for me is to sort of translate this into, well, what is the clinical risk with this drug? And what does it mean to have extra stock in terms of backlogs and stuff like that? But what does this also mean for other things, such as, you know, people's lives and other things like that? Okay, so that's all I wanted to say, but it looks like I'm gotten to a point where it's 11 o'clock. So I've finished on time, but no time for questions, unfortunately. Well, yeah, I don't know if you have some questions.
So I just confirmed that we can extend if some people want to stay.
Okay, sure. Okay, sure. So I've come to the end. I don't know if there are any questions out there. Is there anything in the chat?
Hey, Devin, don't want to leave you hanging out there. Hey,
no
interesting work, but have you considered looking at the differences between the drugs? I mean, they're prescription drugs. They're I mean, we did a bit of work with different pharmaceutical companies, and obviously, you know, for breathing disorders, you know, it's related to humidity rather than sunshine hours. So there could be weather-related things. There could be immediate effects. There could be prescription drugs that are taken very regularly, making it very hard for algorithms to outperform them, other than disruptions in pharmacy. So have you maybe considered looking at the data conditions under which different models do well? Because I think you'll probably find some interesting stuff there.
Yeah, 100%. I mean, so it just the work just reflects, you know, the early stage of it. So the context is they're not even doing some of this. So I've actually, some of the models like the dynamic harmonic regression, like Profit and so on, I actually throw in some holidays and some other effects in there, but you're absolutely right. In fact, another school of thought is actually looking at relationships between different drugs. So using some of the stuff now between cross series models and stuff like that. But absolutely, no, there is nothing else that I've put in there, but that is on the table somewhere. So potentially this is just some sort of research agenda as well. Because I literally engaged with them about 3 months ago. But the benchmark is that they are actually doing absolutely nothing compared to all of that. So. Chair, if there are no more questions, I'm not just going to keep you all here. So I want to thank everyone for tuning out to the session. Hopefully it had, let's stop the sharing. Hopefully it had some value for you, whether it was listening to KNN, Forecasting with KNN, or presentation by our friend from IBM, on using images and networks to forecast for new products, or whether it had to do with forecasting for drug demand. So thank you, everyone. And that's the end of the session.